Well, a very good afternoon to you all, ladies and gentlemen. It's a great pleasure for us to introduce Professor Damian McDonnell to this afternoon's webinar. Damian is a highly accomplished scientist. He's Chief Executive of Science Services Limited. He has a wealth of experience working both nationally and internationally with business and political leaders. He is Director of a London-based Innovation Centre, which is the UK's first investment-focused forum in high technology and high growth businesses. He was Chief Executive of the DDA from 1999 to 2007. He's a distinguished UK scientist, inventor and innovator, and has been appointed by the Queen as an Officer of the Order of the British Empire. And today we'd like to welcome Damian to introduce a little bit more about himself, but also to talk about his very interesting career and with particular respect to the innovation and development of the liquid crystal display technology. Hello to you, Damian, and very warm welcome.
Studied chemistry and was lucky enough to do a PhD in liquid crystals in the early 70s. And that pretty well dictated what happened to the rest of my life, because after that I joined a research team at what was called the Royal Signals and Radar Establishment in Malvern, which was the Ministry of Defence's electronics research base. And I joined their display team, flat panel displays, looking principally at liquid crystals, and spent many years working on developing the materials and the physics of the displays. And then in the latter part of my career, licensing it and innovating it to try and establish connections with the global display industry to both exploit Ministry of Defence patents, but also to slipstream civil sector technology to bring it back into defence. Okay, so that period I worked in liquid crystals was very interesting, because there was a big transition happening where the military were no longer the big investors in key technologies. It started to change so that the civil sector became the lead investors in key technologies for defense. And so we needed to develop a new strategy for slipstreaming civil sector technology. And that was a big thing which we achieved with liquid crystals. And we did it quite consciously. Okay, so that's kind of the background. Because of my success in what you might call innovating technology, I was then asked to set up an agency called the Defence Diversification Agency to more broadly diversify technology from defence into the civil sector to try and boost productivity and in the economy by harnessing defence technology, but also to set up a mechanism for bringing technologies from the civil sector into defence. And that's kind of the spin in, spin out story, which is extremely important. But okay.
No, that's a great positioning. What I'm interested in is to go back a little bit earlier than that, maybe, Damian, and how, who came up with the idea of creating something flat as a picture? Because I come from a cathode ray tube generation of aircraft, and you know, somebody must have sat there and gone, right, we need to make this flat rather than deep. Have you got any sense of how that started?
Yes, of course. I mean, the big driver for flat panel displays was to try and eliminate the bulk and the high voltage of the CRT to enable portable equipment, man-portable equipment. That was certainly the drive in the defense sector, but it was also happened in the civil sector. And the drive came from the appearance of CMOS technology. So there was a general worldwide look to find a technology, a display technology, which was voltage current compatible with CMOS.
Mm-hmm.
And the first people onto that were, among the first were the Sharp Corporation in Japan. And they quickly coupled on to liquid crystals because they found that they were voltage current compatible with CMOS. And they built the first pocket calculator based on an electrohydrodynamic effect that liquid crystals show, called dynamic scattering. But I think if you go to the museums in Sharp, you'll find one of these early LCDs. The contrast ratio was about 3:1. It's horrible.
Mm.
But you know, it met the current voltage requirements for the CMOS circuitry making up the calculator. Now, in parallel, the Ministry of Defense wanted to take the last vacuum tube out of the radar system, and that was the cathode ray tube. And the reason for that was to make the equipment more field portable.
Mm.
Okay, it's pretty hard, you know, carrying around electrical equipment as a soldier, particularly if it requires a kilovolt of power, and you know, a lot of big power packs to deliver that, and it's heavy.
So when you were, sorry,
say again.
So when you were first brought on board to look at the LCD displays, there was a specific product in mind that you were doing the research?
Yes, we were looking at it specifically in the Ministry of Defense to replace the cathode ray tube.
Okay.
Okay, but it took many years to develop liquid crystal technology to the point where you could get the kind of complexity and contrast that the good old CRT offered. It was a very good display. So, sorry, Paul.
So sorry, you mentioned in the sort of preamble that you you'd done some research in this in the early 70s, I think, as part of your degree. And what led you into that area of research? Because that's often, you know, as you arrive out of university, you're looking at what you want to do with your life. You obviously found something that's really motivated you and been very worthwhile.
Yeah. On the very last day of finals, there was a job advert on everybody's desk for a PhD position with a chap called George Gray. Now, George Gray is one of the global father figures of liquid crystals and liquid crystal technology.
Mm-hmm.
So it was a lucky break. I just happened to be at the right university at the right time. And I also had got on well with George Gray, so that's important, is if you don't establish a relationship with the person you're going to work with for 6 or 7 years, it's not going to work. He and I got on very well, and I was rather good at what was called then molecular engineering. That is the design of molecules that had specific electric and physical properties, and which were needed by and defined by the electronics and physics requirements of the displays. So there's quite a lot of very interesting molecular engineering and fluid engineering. Fluid engineering is the mixing of those molecules to provide fluids which operate within the voltage current parameters of the display circuitry, and also provide really good contrast and color.
Mm-hmm.
So now in terms of getting an optical effect, that was established, a good optical effect beyond dynamic scattering. There came the ubiquitous twisted pneumatic display, and that came from Switzerland by 2 scientists working for the watch industry. And the watch industry were very interested in liquid crystal displays because at that point they had just introduced electronic timing circuits based on quartz. And the display they were using was an LED. You may remember them that they used up the silver oxide batteries rather quickly. So they had a little button on the side which you pushed when you wanted to read the time, and the rest of the time the display wasn't on. And that wasn't, so digital electronic circuits for displays became quite popular in the 70s and became the first early user of LCD technology, taking advantage of the higher contrast that could be achieved with the twisted pneumatic effect. And it was entirely compatible with a year plus of lifetime for the early silver oxide batteries, the little button batteries. And it meant your display could be on all the time. Okay, but now those attractive properties were then imported into calculators, and calculators became more and more important and more sophisticated. The early versions that were produced by Hewlett-Packard, Sharp, Casio, and others, they also used LCDs. And the challenge in going from a watch to a calculator was to get more information content into the display. And that presented quite a challenge. So because the watch displays were simple enough to drive, you could, each picture element was an individual capacitor, and you could switch the voltage on or off to it in direct drive mode. Once you started to add more picture elements, you had to go to time sharing of electrodes, which is called multiplexing. And multiplexing a display, you had to fast scan down the rows, switching the element on and hoping it would stay on long enough before you had to go back and refresh it. And that set particular parameters on the switching characteristic of the liquid crystal. And there was a fundamental limit which limited it to about 16 lines, maybe 32 line displays. So the next big advance was to go from those early calculators to a new display that enabled laptop computing. That was the first VGA display, and that required a development going from twisted pneumatic to what was called super twisted pneumatic, which was a way of changing the voltage transmission response of the display to sharpen it up, which allowed multiplexing levels which were much higher. Unfortunately, contrast dropped. But that contrast, low contrast, relatively low contrast display, nevertheless enabled portable computing for the first time. So you can see, go on.
I was just going to say, Damian, I mean, you really give me a little moment of down memory lane, because I can remember my wasted youth when I was trying to write rude words on my calculator by turning it upside down on the little LED displays. And that was really my first introduction of this next technology that was, for us, it was the Sinclair, it was the real innovative part of it. And so I'm really fascinated to hear it. One question I was just going to ask is, you mentioned that it took a lot of resource and a lot of effort. How big were the teams driving these various, because it sounds like there's lots of small parts of this technology that was growing. What did the teams look like, and how was that grown?
Okay, they were growing, and the number of publications were growing exponentially through the 70s, but really took off in the 80s. So our team was about 20 people, but we had contracts at numerous universities throughout the UK. So we were probably a team of about 100, which was pretty well insignificant compared to some of the Japanese companies and the investments they were making. But so, you know, the teams started to grow really quite large. We and my team, which was about 30 to 40 people by the 90s, we joined forces with Sharp and worked on joint programs. And one of them, aimed at a 40-inch display, had about 100 people working on it across material science, physics, and engineering. And you know, it's quite interesting that I'll probably come back to it in terms of the question you asked, Amir, about the innovation path, because that is really quite interesting when you go back and analyze how LCDs emerged, to look at what's needed really to support and launch an innovation objective like getting a disruptive technology to CRTs, because that's what LCDs became.
Yeah, so just to take you on to another aspect of it, really, Damian, you talked about there kind of this emerging need for the development of LCDs from several fields. People recognize the need for them to move technologies forward, to shrink them down and to lower voltage, but also some of the issues with the response rate, luminescence and contrast. When you started working on the LCDs for the application that you were looking at, and I'm thinking about in terms of innovation here, because that's a really interesting story. When you started working and you had your team together and it was small, of around 20 people, what were the initial big challenges that you faced in trying to make this technology a reality to serve the function that you had in mind?
Okay, very early on, to make the twisted pneumatic device invented in the early 70s, to make that work, you had to have a liquid crystal that had a specific viscosity to make the response time needs. Liquid crystals are activated by putting a field across them, but to switch off, they rely on surface anchoring forces. And those are viscoelastic forces. So you have to design the liquid crystal to have the right kind of viscoelastic properties. You also have to get it to orientate in the correct direction in the field, and that's defined by its dielectric permittivity, which in liquid crystals is anisotropic, meaning that it has two values depending on the orientation of the crystal. And the difference between the two permittivities is called the dielectric anisotropy. So to get the voltage rating right for the liquid crystal, you had to have a pretty high dielectric anisotropy, about 10, with the right viscoelastic properties. And because it's a light modulating, it doesn't emit light. It rotates the plane of polarization of polarized light. Okay, that's how it works. It had to have specific optical anisotropy. So it had two refractive indices, as it had two permittivities. And you have to create a cell that had the right optical path length defined by the delta N, the birefringence, so the difference in the two refractive indices, and the thickness of the cell. So all of those physical parameters had to be tuned. The liquid crystal had to be tuned to fit the cell to get the optical effect and the electrical effect. And because we were modulating light, it had to be light stable. And if you've ever looked at faded curtains in sunlight, you'll know that organic materials tend to react with sunlight. So we had to develop liquid crystals which were chemically quite inert to light. So those were the early challenges, which were largely solved through the 70s. The 80s was all about fine-tuning the voltage transmission response by additives and by slight changes, engineering changes to the parameters of the cell, the alignment, material, thickness of the cell, and the types of Polaroid. Okay, so those were the early kind of breakthrough advances which were needed to make it a viable display technology. Once it was viable, the question then was, how do we get it to the same sort of complexity that you can handle the same kind of imagery that a CRT can handle? So we had to introduce color, and we had to introduce more complexity. So I think current displays operating at high definition levels are up around 1280 by 1024 pixels. And that is achieved by not multiplexing directly the liquid crystal pixel elements, but by addressing transistor elements that control the voltage across every single pixel. So today's displays are an amazing achievement of large-scale integrated circuits. The displays are made on production lines where the glass sheets that they process are 2 by 3 meters, and they are bigger, may even be bigger today. And they go through a number of processing steps to build each picture element into it a thin film transistor based on polycrystalline silicon. So what enabled all of that was further progress in semiconductors. Okay, so through the 90s, we then moved from direct drive and multiplex systems into active matrix driven systems. And that was the game changer.
I was going to say that I can remember in my sort of teens or the late 70s, whereby I was typing in information on cards to drop into computers and to run programs. Were you frustrated in those early years that you hadn't got the processing power in order to deliver your technology, or was it that your technology kind of followed hand in hand with the development of the sort of a computer at the time, really, which was in its relative infancy?
Yeah, the liquid crystal technology was working alongside CMOS and solid state circuitry, because as more and more portable equipment was demanded, and better computers, and larger scale integration. So larger scale integration on single crystal silicon enabled more efficient, energy efficient computers and more sophisticated computing. What was required to run along with that was a more sophisticated display, because that is the man-machine interface of choice for computing. Okay, because it's the broadest bandwidth way of communicating with humans is through their sight. Okay, so the two worked hand in hand. So looking at this, you will find that most of the people pushing liquid crystal technology, pushing the boundaries, were also pushing the boundaries of computing. And you know, after the calculator and the laptop computer came the personal digital assistants, PDAs. And then the no-brainer was, well, why not combine that with the chip in a mobile phone? And then became smartphones, which was the combination of portable phone and a computer. And of course, all of that demanded the man-machine interface, the display, to be more complex, to offer color, to offer speed, to offer a range of operating temperatures, because the phone couldn't stop working in the winter or the summer. Okay, so that's how things progress. But running alongside of that, there were developments in Polaroid film. So you had a number of large Japanese corporations, Sanritsu and Nippon and others, all working on complementary technologies to enable LCDs. So, not least of which was getting flat, smooth glass with a transparent conductor, which, based on indium tin oxide and improved float glass techniques, because if you're working as they were with cell gaps to get optical path lengths well tuned, you'd be looking at active matrix panels having a cell gap of maybe 5 or 6 microns. So you couldn't tolerate any lumps or bumps in there. It had to be pretty smooth, which was challenging. But by then, there was sufficient impetus behind the technology. In other words, enough market pull, because people wanted to get out, and there was a fast turnover in improved personal digital assistants, improved telephones, smartphones, and then the technology was carried to the point where we could begin to attack the price of cathode ray tubes for television.
So it's very interesting, Damian, to hear you mention about all the different kind of disciplines which were involved in developing the technology. And I think that's what makes this LCD story so interesting, is that the multifaceted effort that had to take place in order to bring this development together. It's very interesting to think about when you're talking about developing an innovative product. The development is, as you know yourself, is very rarely linear. And it comes and kind of stops and starts in some ways. When you were developing the LCD technology, maybe going back maybe to when you had you were looking at the material science started, were there any points at which you felt like you hit a breakthrough, or walls that you felt like you were going to come up against that you then took maybe a leap to overcome?
Yeah, first thing I would say is that another good thing when I was doing my research was that I was being fed problems constantly that the industry were facing. Mm-hmm. So I was looking at how to solve those on a daily basis. Okay, and it would be things like how do we lower the melting point? Mm-hmm. How do we improve the dielectric anisotropy to get lower voltage performance without compromising switching times? Okay, now those very detailed specifications were made available to me from the industry via the chemical company that we licensed the technology to, because they were marketing it and getting a lot of feedback from the Japanese and early American industry that were trying to use these materials. So did I have any breakthroughs? I had a number. So if you look at my patent record, it's vast. And that wasn't because I was very clever at thought experiments. I was responding to market requirements. Mm-hmm. And that's the key to innovation. For innovation to happen, you must have a consumer.
Right.
Okay.
Sorry.
I was just about to say another, the piece that I always say on this is that an individual can invent, or a few individuals, but innovation requires huge teams of multi-disciplines. And so, myself, I started into this as a chemist, but stroke material physicist, but along the way, worked on electronic engineering projects and also worked on process engineering, how to build an LCD from a sheet of glass, and that required setting up clean rooms and the like. So that was a big thing for me. And I kind of grew as a person and as a scientist, technologist with the technology, but it was always in response to market demand.
When I do a bit of lecturing on aircraft operations, Damian, and sustainable aviation, and one of the points I try to get across to the PhD candidates there that is the lead times that this has taken, and you've taken us through a journey that's probably spanning about 20 years at the moment. So two questions sort of spring to mind. One is, emotionally, that's a long time to be wedded to a process that you hope will have that monetized outcome, really. And how secure were you as you were going through the process that you were continually going to have that investment to pay for the teams, to pay for jobs, to pay for the next bit of technology that you needed to bring in?
Yeah, well, you're quite right. There's an innovation lifetime or turnover. It's about 10 years, from being on the bench to getting into the marketplace is about 10 years. With LCDs, to go from a liquid crystal into TVs was about 30 years, but it was about 10 years to do watches, 10 years to do calculators, laptop computers, desktop displays, and then LCDs. Okay, so they were the journey time. I always explain to people is about 10 years from seeing an effect on the bench to turning it into product, and that's it's a bit longer if it's a drug, because it has to go through detailed testing, and that's reflected in the way you can extend the patent life of a drug. Let's take account of that. But in most physics-based innovations, it's about 10 years. That's about the cycle time, bit less, bit more. But with LCDs, we went through 3 waves, and rode on the back at each wave of all of the support technologies that went before. So we had solved the conducting glass problem, we'd solved the high quality polarizers, we'd solved the alignment technology for the LCD, we'd solved the problem of how to do color dots and color matrices within the display. Okay, so now how did we fund that? Well, a lot of the money in the early days came from defence. And certainly most of the UK's effort was funded by defence, and that's because there was an established defence requirement. Okay, what we realised was there wasn't enough money in the defence budget to fund the whole development just to replace a radar tube. And that's when this idea of slipstreaming came in, which was license the technology out at an early stage and let the civil industry begin to interact with it and invest in the enabling technologies. Okay, and we did that very well. And it wasn't until the 3rd wave of innovation that we really got what we set out to achieve, which was a color display to replace the colored CRT. And that, you know, so it's quite interesting how we recognized that was happening and how we changed tactic. And it wasn't always, excuse me, I've got a developing frog here, going here. It wasn't always appreciated by the defense industry in the UK at that time that we were licensing technology beyond them. But it was my view that there was insufficient commercial commitment from the UK industry to get us to where we needed to be. Mm-hmm. And that's why I went overseas, because they had already begun, the electronics companies in Japan, to invest very heavily in the enabling technologies, particularly the electronics computing technology.